In this video, we'll address some of the questions you asked in the exit survey from last time, as well as some of the things I noticed from your homework on factoring. So this is factoring questions answered. The first thing we'd like to address is called factoring completely. And we haven't really seen this word completely as much, so here's what it means. In the homework assignment, there was one exercise that asked you to use the generic rectangle to factor negative 8xy plus 24x squared. And many of you did wonderful answers. And here are some of your answers. You had negative 8xy plus 24x squared equals negative 8 times xy minus 3x squared. Because you factor out the 8 as their common factor. And some of you wrote 4x times 6x minus 2y, because you notice that 4x is what they have in common. And also some of you wrote 2x times negative 4y plus 12x squared. As you saw, 2x is what they have in common. All these are correct ways of factoring. However, they're not what we call factoring it completely. When we say factor completely, that means we have to take out what they have as a common factor, the greatest common factor they have. So in this case, well, numerically, they have 8 as their greatest common factor, between 8 and 24. And for the variables, I have an x here and an x squared here, so x is also part of the greatest common factor. So for factoring it completely, negative 8xy plus 24x squared, the greatest common factor is negative 8x. You can say 8x as well, but here we're going to go with a negative sign. It'll make our other factor a little easier. So here you get a y plus 3x. Actually, minus 3x. Because we need a negative here and a negative here to get to positive 24x squared. So this is the greatest common factor, and that's why this whole factoring is called factor completely. So factoring completely simply means I have broken down a polynomial so that nothing else can be factored. They have been broken down as far as they can. Let's take a look at another example. For example, if I want to factor 4x plus 8 times 3x plus 9 completely, well, I need to factor completely this one. This is actually already factored, as some of you might notice. It is already in 2 binomial factors. However, inside each binomial, they each have their own common factor that has not been factored out. Here is the 4, and in the second binomial factor, 3 is the common factor. So if I factor out the 4 for the first binomial, then I will have x plus 2 here. And if I factor out the 3 for the second binomial, I'll have x plus 3 here. So the 4 and 3 together multiply to be 12. Then I'm left with x plus 2 times x plus 3. And then we notice that actually there are 3 factors here. 12 is a numeric factor, x plus 2 and x plus 3 are 2 binomial factors. So this is what we call factoring completely. Now, this actually goes into the second question that some of you asked, is it possible to have more than 2 factors? And the answer is yes. You already saw from the last example that 12 was a common factor and a numeric factor, so that makes 3 factors. Let's take a look at another example. If I want to factor completely, and I'm going to start mentioning this word completely more and more frequently, this polynomial, x cubed plus 5x squared plus 6x. Well, let's take a look at this. The first thing I'm going to look for is, I notice that this is a cubic polynomial. So that is sort of like a sign for me that there's probably going to be three different factors. Although sometimes for a cubic, we might have two factors. One of them is being squared. But in this case, we're going to look for three factors here. And the first factor that I notice is the greatest common factor that all three of them have. If I were to put those in a box, in a generic rectangle, then I can factor out an x here and be left with, here I need x cubed, 5x squared, and 6x. Well, if I factor out an x, which was what they have in common, then I'll have x squared, 5x, and 6 here. So if I do that, then I'll end up with x times x squared plus 5x plus 6. So far, I've got two factors. One is a monomial, and the other one is a trinomial. So let's take a look at the trinomial here. Well, this trinomial, can I set up my x diamond so that I have two numbers that multiply to be 6 and add up to be 5? And what will be the two question marks that will add up to be 5 and multiply to be 6? Well, I have my x here and two other factors. In this case, the two question mark will be 2 and 3. So I'm going to end up with x plus 2, x plus 3. And so here we end up having a polynomial that can be factored into three different factors. And some of you actually even wondered, is there a visual model to represent this type of factoring? And the answer again is yes. Well, we can't use the generic rectangle anymore because the rectangle only covers a quadratic, which is the highest degree is 2. And here we have a highest degree of 3. So what do you suggest? I'd like you to pause the video for a moment before you continue and think about what could be a visual model to represent this type of factoring. Okay, so did you think about a way to represent this visually? If you think about the term cubic polynomial, then it might give you a clue that we're going to use a three-dimensional box or a cube to represent this factoring. Again, I have x cubed plus 5x squared plus 6x, and I managed to factor it into three different factors here. If I think about the generic rectangle first, which will cover my x plus 2 and x plus 3, well, how would that look? I will have a 2 by 2 box, and that's going to be x and 2 and x and 3 here. And now, what does this x do here? Well, that's like adding another dimension. If I were to add another dimension to this generic rectangle, I'll create a three-dimensional box. And the width of this box is going to be x. Now for homework, you're going to explore where the x cubed, 5x squared, and 6x can be represented, or how they can be represented using this cubic model. The third question that some of you asked is that, is there an efficient way, a more efficient way to factor a polynomial or quadratic that has more than one x squared? A quadratic with more than one x squared. And the answer again is yes. And we're going to take a look at one of the examples that you did for homework last time. So from homework, there was a question that asks you to factor 2x squared plus 3x minus 9 using algebra tiles. And this one was a little bit challenging because you got -9 and +3 here. So let's actually review the algebra tiles first. If I have to get two x square tiles. Notice how I'm drawing the x square tiles like they're really x square tiles, not just x tiles. And then I'm going to end up with -9 unit tiles. So one way to line up -9 unit tiles would be to do a 3 by 3 array. So if I have a -9 tiles 3 by 3 array here, and notice that they're all negative here. Okay. So if I set it up this way, then naturally I'm going to end up having a 3 x tiles here and 6 x tiles here. But I only need, at the end, 3 x tiles, not 9 x tiles. So that means some of these x tiles have to be a negative ones in order to cancel those out. Well, I have 6 positive x tiles. If I have -3 x tiles, then these become negative. That will actually cancel out the 3 x tiles. So that right away tells me that I have my dimension xx, -1, -1, -1, and x, 1, 1, 1. So the factoring for this will be 2x minus 3 times x plus 3. So as you can see, using the algebra tiles, it's very visual and clear that I can get a way to factor this. And it is a little bit long because I have to draw out all the tiles. So here is a good way, shortcut. So I have 2x squared plus 3x minus 9. And we're going to use the generic rectangle here. So again, I'm going to set up a 2 by 2 box. And the first two things I'll fill out is 2x squared and -9 here. Just like when I was doing the tiles, I drew 2x squared tiles and 9 -9 unit tiles here. So here I notice that whatever the box I fill in for here, these two, when I collect them at the end, they have to add up to be 3x. So I know these two question marks have to add up to be 3. Well, what do they have to multiply to be? Notice that all the diagonals on the generic rectangle, they're going to be multiplied to be the same. So 2 times -9 is going to make -18, which means these two question marks are going to multiply to be -18. So what are the two factors that will give of -18 that will make a 3? Well, I have 6 and -3. So here I'm going to fill in 6x here and -3x here. And notice here that the 6 and a -3 multiply to be -18 as well. So now I'm up with a generic rectangle all filled in, 2x squared, 6x, -3x, and -9. And now my job is to figure out the dimension. And I'm going to look at the top row. What they have in common as the greatest common factor is 2x. Here will become x and a 3. And the bottom row, they have -3 in common. And so again, my factoring now becomes x plus 3 times 2x minus 3. And it's exactly the same as our result from the algebra tiles. So this is just a little bit faster and more efficient way to do that, factoring a polynomial, a quadratic here, that has more than 1x squared here. And let's take out another example. Let's do 3n squared minus 8n plus 4. N is the same as x. So again, I'm going to set up my generic rectangle with 3n squared and a 4 here. And the diagonal here, I notice, is going to multiply to be 12. And whatever the question mark I set up, it's going to collect out to be -8n. So in my diamond, they multiply to be 12, add up to be -8. So what are the two factors of 12 that will add up to be -8? Well, -6 and -2. So I have -6n and -2n. And now they also multiply to be 12. So then again, you're going to think about the row and the bottom row separately. Having 3n squared, -6n, -2n, and +4. Top row, will have 3n in common, n and negative 2. Bottom row is going to have negative 2 in common. And so my factoring turns out to be 3n minus 2 and n minus 2. So again, you practice some more with homework using this technique, and let's see how it goes. We'll come back to discuss more questions that you have next class.